In this YouTube Principal Component Analysis, PCA, which is the Representative Dimension Reduction method, has been produced into 2 videos which cover the theory and the coding sections. If you are interested in the theoretical part, please refer to the first video. In this second video, we will explore what results can be obtained from PCA and how to implement it through coding. To summarize, Principal Component Analysis is an unsupervised dimension reduction method that selects the principal components with the highest variance in the data. Here, since variance means the largest eigenvalue, so the principal component is chosen as the eigenvector with the largest eigenvalue. As shown in this illustration, the 2-dimensional data points represented by x1 and x2 are projected onto a 1-dimensional axis called z1 based on this principle of PCA, achieving dimension reduction. As mentioned in the previous video, in PCA, Principal Component Analysis, the variance of each principal component is equal to its eigenvalue. For example, when we obtained eigenvalues for 4 principal components, z1 to z4, as 3.5, 1.5, 0.3, and 0.2, respectively, if we divide each eigenvalue by the sum of all eigenvalues, we get the proportion of each component's variance to the total variance. Z1 explains approximately 63% of the total variance, Z2 explains around 27% of the total variance, and when combined, they account for 90.9% of the total variance. With the obtained proportions or eigenvalues as the y-axis and the corresponding principal components as the x-axis, we can plot a graph known as a scree plot. This scree plot helps us determine how many principal components should be chosen. The point on the scree plot where the y values show a distinct change and flattens out is called the elbow point. We should select the principal components to the left of this elbow point. Another method is to choose the principal components that together contribute to a cumulative proportion of 70% or more. In this case, since the combined value of z1 and z2 exceeds 70%, we select these 2 z1 and z2 as principal components. In Principal Component Analysis, the biplot overlaps the score plot and the loading plot. Firstly, the score plot allows us to visualize all the data points projected onto the selected principal components, providing insights into patterns and relationships within the data. Specifically, it displays the proportion of total variance represented by each principal component in the x and y axis. In this case, the first 2 principal components preserve 95.9% of the variance, with contributions of 84.1% and 11.8% respectively. For instance, in the case of the iris dataset containing a total of 150 data points, if we represent different species with different colors on the score plot, we can easily observe that the 3 species are grouped and distinguished from each other based on the projection of their data points onto these 2 principal components. The loading plot visualizes the arrangement of features on the selected principal components. This allows us to identify which variables have the largest effect on each component. The absolute value of each feature's position on the loading plot indicates the magnitude of its influence on the corresponding principal component. A larger absolute value suggests a stronger influence on the corresponding principal component, while a value closer to 0 indicates a weaker influence. Looking at the loading plot for the iris dataset below, we can interpret that petal width, petal length, and sepal length are positioned in the positive direction of PC1, indicating that they play a significant role in PC1. On the other hand, sepal width has a more significant impact on PC2 compared to PC1. Alright, let's wrap up the theoretical part of PCA we have covered so far and move on to implementing it with code using the iris dataset. You can find the Jupyter Notebook file on GitHub, which you can download and run directly. To perform the coding, we'll need to import several libraries: NumPy, Pandas, TrainTest_Split for data splitting, MinMax Scaler for normalization, Matplotlib for plotting, and PCA for running principal component analysis. Firstly, we load the Excel dataset and store it in the variable df, then convert it to an array for calculations. Next, we'll assign the columns representing the three species, Setosa, versicolor, and virginica, to the Y dataset. For the X dataset, we'll perform normalization using MinMax Scaler, and then assign the values to it. We also save the column names from the Excel dataset in the call_names variable, which will be used later when plotting the graphs. N_components represent the number of principal components, and since PCA is a dimensionality reduction method, it should be smaller than the number of X data points. In the case of the iris dataset, which has 4 X data points, we have inputted 3 as the number of components. As PCA is an unsupervised learning method, you remember that it only uses the X data for training. After that, using the explained_variance_ratio_ command, we can obtain the proportion of total variance captured by each principal component. Printing this information, we can easily see that the first principal component explains about 84%. The second principal component explains about 11.7%, and the third principal component explains about 3.4% of the total variance. Plotting these proportions with the corresponding principal components on the Y and X axes, respectively, we can obtain the scree plot like this. Furthermore, since the two principal components explain more than 95% of the total variance, we will select only these two components to plot the graph. We name the two principal components as PC1 and PC2. To set the species as the legend, we add the actual species data, which is Y data, as an additional column with the name target. This allows us to plot the graph with PC1 and PC2 representing the X and Y axes respectively, and use the target column to set the species as the legend. Based on these PC1 and PC2, we can plot the graph and obtain a score plot like this. To distinguish the three species, we use different symbols, triangle, square, and circle, to represent Setosa, versicolor, and virginica, respectively. With this plot, all 150 iris data points are projected onto the two principal components, and we can easily identify the species to which they belong. As a result, we can see that the species are relatively well clustered by the two principal components, indicating that these components effectively capture the differences between the species. Finally, let's draw the loading plot. Here, in the variable call_names, we have the names of the features. We will assign these names to the X_features variable. Since we have 4 features, we will use a for loop command to repeat the process 4 times. In the first for loop, we will provide the coordinates, and in the second for loop, we will provide the feature names. By doing this, we can obtain the loading plot as shown here. As explained earlier, this loading plot allows us to see how each feature influences the two principal components, PC1 and PC2.